Yeah.
Yeah, so we are very happy to have Vishwa with us. Vishwa did the BSc from Madras University and MSc from Anna University and PhD from IISc. Incidentally, which is the same path that I took, Vishwa. So I also was a BSc from Madras and MSc from Anna and PhD from IISc. And Vishwa then spent some time in Harvard and MIT as a postdoctoral fellow before coming back to India and becoming a faculty member at Mandi. And I have colleagues who tell me that I am a blind physical metallurgist because I never looked through electron microscope. But Vishwa is probably one of the fine microscopists that I know, and so he certainly has a up close view of physical metallurgy than most of us have. So we are very happy to have you with us, Vishwa. So, and we are looking forward to your talk on strain engineering. And before I hand over the mic to Vishwa, you can keep yourself muted. I'm also going to stop video, so only probably Vishwa's video will be on. But at any time, if you have any questions, please unmute yourself and ask or post it in the chat. We will ask Vishwa the questions. He wants to keep the interaction during the talk, so don't hesitate to ask any questions. Vishwa, it's all yours.
Yeah. Thanks, Guru. I think thanks for inviting me. In fact, probably like after a long time, I'm going to give some research talk. And in fact, like as correctly said, my connection with Guru probably will go back to maybe 2002 and 3. Very like just after I joined IISc Bangalore, I used to interact with you. Of course, I also interacted with Professor Preetha for many times. Again, glad to connect back and so on. So I, in fact, like based on brief interaction with Guru about the seminar series, I think it's an excellent one. And I'm also glad to note the previous speakers, especially after Professor Rajesh Prasad and so on. So I'll see like that I can do justice to the topic and the micromechanics group that you are actually offering this particular seminar series. As pointed out by Guru, I have a little bit of physics background. Later on moved to materials. Always enjoyed interacting with the metallurgist. I do believe the conventional knowledge of metallurgy can be very well used for many of the functional materials and so on. So this is our campus, just to advertise. It's a nice location. In spite of COVID, we do see a lot of tourists coming these days. The right one, what you see is a 2014 picture. That is the time I joined IIT Mandi. We have two campus, south and north. It's like a 4 kilometers away from each other. And now, like 2019 or so, if I just zoom only the north campus, where you see like many classrooms, apartments, and so on. So it's a very dynamic campus. I'm sure you would enjoy when you visit. I'll always keep this invitation, invariable. Looking forward to interact with as many of you, possibly at IIT Mandi when you get a chance. So, like in our group at IIT Mandi, we are essentially like working on these three aspects. I would put together called nano manufacturing and nanomechanics. The first one, I think that is what the picture that probably would have noted in my abstract, wherein we are trying to measure the mechanical properties across the phase transformation in vanadium dioxide. So of course, we can actually have coexisting phases. Let me see that I can open the pointer. So like the phase transformation can be triggered by multiple stimuli. We do often use the heating or temperature in order to induce the phase transformation. So we can use the nano indentation to measure the properties as a function of temperature with a heating setup and so on. It is also possible to stabilize both metallic and insulating, otherwise rutile and monoclinic in terms of structure. It is possible to stabilize both the phases at the same temperature. In fact, that actually takes care of any variation you might introduce due to the temperature. Without heating at same temperature, we can actually go from metallic domain to domain what you see as a gray color and a white or yellowish color. These are the two different phases. That is a one way we can precisely measure the mechanical properties. I also try to probably convince you nano indentation can be used for not just the elastic modulus or hardness or fracture toughness. We could also possibly do something more. It is possible to even actually measure the actuation across the phase transformation. In fact, that is what's shown here. The spontaneous strain as a function of temperature across the phase transformation from monoclinic to rutile. So my talk, like pretty much I'll try to focus the three questions that I posted in my abstract. I'll actually revolve around the vanadium dioxide. Otherwise, taking this as a model system, I'll try to answer or at least initiate some discussion. I'm not very sure if I have a time. I will also like to at least initiate some discussion about the 2D materials during the growth, and also like with respect to many triggers. It is also possible to induce the phase transformation and also achieve coexisting phases. Especially if you look at this particular image here, it is a fluorescence image. In optical image, we don't see any contrast, all are uniform. But in fluorescence, you can see there is a dark region and a like bright region. Otherwise, more fluorescent and less fluorescent in a triangle form, very nicely self-organized. So this kind of phase coexistence and also phase manipulation has to do with the strain and also defects and substrate interaction and so on. We have some results. I will see whether I can at least initiate. We also use nano indentation for sculpting, like lithography. We can actually use nano indentation, induce locally, like of course strain. And in extreme cases, it is possible to remove the material by selectively doing indentation. What you have seen here, IIT is essentially the nano sculpted area wherein we can remove the 2D materials, in this case, WS2 monolayers. The last spot, again, the CNT growth, it's well known for a long time. In our group, we are trying to also see what is the mechanics involved in the CNT growth, and also after growing as a forest, the collective behavior, like mechanically, how do we make a robust structures? There are also some work with respect to CNT. Just if there are any research scholars, I just like to mention this. If you look at the publications, the VO2, of course, relatively we have a less number of publications, right? It's also like 1959, the first time VO2 has been known for phase transformation. There are a lot of 4 or 5 decades of work, mainly like dominated by the physics community. And again, we are trying to find out, is there any still some fundamental problems, especially coupling the mechanics with the phase transformation, strain engineering with the phase transformation? Any questions can be answered. There are plenty of work already done, but I do see there are scopes to do more. 2D materials, of course, relatively new, 2010. There are several things, of course, not clear. We can keep explore on almost like on a monthly basis, if not daily. And relatively, I would say easier to publish papers. And CNT 1991, right, Ijima discovered, and of course, in a transmission electron microscope. There are some fundamental questions. Same time, many applications already well established. It is also possible to find a problem. So what I'm trying to emphasize here is the material or the phenomena, phase transformation. I don't know, like somebody can correct me, right? Probably century old. Still, there are fundamental problems which needs to be answered. So irrespective of the material that is old or new, there is always scope to do a good science and possibly connect with the newer engineering applications. I would like to probably thank my group members. Of course, I can only speak these days. These are the hardworking, sincere students who actually contributed for the work that I'm going to present. We have 3 of them already graduated, and 6 of them at present actively working. We do have some of the facilities. We do nano manufacturing. When I say a lot of gas phase reaction, vapor phase, typically involving chemical vapor deposition, RF DC sputtering, atomic layer deposition, and we do focus on both nano mechanics by indentation And also we do measure the basic nanoelectronics or photoconductivity and so on. Let me just remind, these are the three tasks that I'm planning to achieve. The first one is, how do we visualize the phase change induced actuation in nanoscale cantilevers? There are many work already, right? By resonant frequency, by optically also it's possible to visualize. There are many ways to measure the actuation. But is there any way to actually visualize the actuation across the phase transformation, especially from different forms of materials, be it thin films, nanostructures, and single crystals? And the second point is, how do we reliably measure the mechanical properties across the phase change? And third one, can we also manipulate the phase transformation with the aid of strain, and especially to manipulate the transient temperature and also threshold voltage? The reason I'm saying a transient temperature and threshold voltage, many of these phase transformation are sensitive to temperature, light, applied like a strain or stress, and also electric field. So that way it is also a big a landscape where we can try to manipulate this kind of threshold, either temperature or the directly the voltage for the electrically triggered phase transformation. This is a one slide introduction just to show why phase transformation or the phase instability is interesting. In my opinion, as a material scientist, for structural application, right, like structural steel, it's a well established. We have a, I would not say all the problems are solved. Even steel, there are still a problem with respect to phase transformation itself. But we have a relatively a stable system. But many of the other applications really require something smart, right? Smart properties. The properties can be tuned, reversibly tuned. That way, the instability is actually a key rather than having a stable or inactive material. So I'm just taking one example, in this case VO2. The VO2 resistance, for example, or optical properties like optical transmittance can be reversibly tuned by heat, voltage, right? Just by shining light. Right? You can actually see there is a 4 to 5 orders of change in the resistance, and the material can almost go from 70 to 80% of change in the optical transmittance. So the instabilities actually makes these materials more interesting due to the tunable properties. And also some of this phase transformation are known to be stable, stable in the sense up to 10 power 6 to 8 cycles, reversibly we can actually tune their properties. And the time scale is another interesting aspect. Some of this phase transformation is also found to be typically at least nanoseconds. Right? There are also studies showing that even picoseconds, the transport properties can be manipulated, but there is a structural relaxation that follows the electrical properties. That way, at least hundreds of nanoseconds is really a fast phase transformation we can reversibly use. There are many applications. I won't be able to cover all of them, including many of the actuators, strain sensors, even for phase change based transistors, switching application, and so on. And this is also if you compare, if you want to make actuators, in this case, you can see the photograph, how this can be used as a gripper. The phase transformation in VO2, structural phase transformation, it goes from monoclinic to tetragonal around 68 degrees Celsius. So clearly you can see during the phase transformation, due to the volume change, it is possible to use them as a gripper, because you will see each and every arm here going to deform. And this is also compared with other materials, the displacement to length ratio, for example, for a cantilever if you are making. Among the many other cantilever materials like piezoelectric, bimetallic strips based on thermal expansion, or shape memory alloys, and so on, vanadium dioxide seems to be showing a very good displacement to length ratio. Even when you have a short cantilevers, it can actually show a very good actuation or the tip displacement. So some of this application, what I'm showing here, as a result of phase transformation, there is a volume change. Associated stress can be used for actuation purposes. That is what shown here as a cantilever, the cantilever deflection, how it can be reversibly tuned. On the other hand, the phase transformation also can be induced by the stress or strain, which means it can be used also like a strain sensor. Since there is a associated electrical properties, for example, the current can be reversibly changed when you are applying a compression or tension, which can be a very sensitive strain sensor. Let me just give you a probably basic introduction about how do we actually visualize or measure the stress or the actuation. For thin films, it is a well established, right? The famous Stoney's equation. This is again a Nick's paper in 1989. We all know that thin films are always under stress, right? Freestanding is free from stress. The moment you try to deposit, attach your thin film with respect to the substrate, they are no longer free, either to expand or contract. So obviously the thin films would impose some stress on the substrate. You can see here, the substrate itself can have a very small curvature. So what do we do for a thin film stress measurement? Before and after thin film deposition, typically we use laser scanning method to measure the curvature. It's a very sensitive tool I have used for at least several years. And once we know the some of the parameters, of course, we need to know. The assumption is your substrate thickness has to be much larger compared to the film thickness. So once we know the film thickness, substrate thickness, the radius of curvature is something we are measuring. We have a biaxial modulus. We can measure thin film stress directly from this particular method. The key here is this particular measurement also can be done as a function of temperature. So after depositing a thin film, for example, the thin film which is not attached, it is going to be stress-free. The moment you attach to the substrate, of course, there is going to be a stress imposing a curvature. Now, imagine the thin film, in this case, vanadium dioxide or a shape memory alloys like nickel, titanium, they're going to undergo phase transformation during heating and cooling. So because of the heating cooling induced phase transformation, there will be a volume change. That volume change would induce reversible change in the curvature. The picture here, I think probably it's a exaggerated picture. We will not find such a large curvature change. The idea is VO2 during the phase transformation, what is happening? It is going from compressive stress to the tensile stress, because there is a volume shrinkage that is happening across the phase transformation. So that is what causing this tensile stress development during the heating. So ultimately, after measuring the curvature by putting the other parameters, we will be able to clearly get the stress as a function of temperature. So you can see here the red color marked triangles that correspond to the heating, almost like 300 to 400 megapascals of tensile stress is developed when it is going from monoclinic to tetragonal. And during cooling, it is perfectly reversible. So this is something known for a long time. Then in fact, we tried depositing thin films and asked ourselves how many cycles we can actually switch the stress. When I'm saying stress switching, we are able to reversibly tune from compressive stress to the tensile stress. So we have done the cycles for around 100 times, which is plotted in the other plot here. I'm showing only the last 20 cycles. We can see how stress can be reversibly tuned between 50 degrees Celsius and 90 degrees Celsius. So it is extremely stable. And at the same time, the transformation stress can be also controlled. So we have, for example, gripper or some actuators. We want to actually control specific stress or specific strain. In that case, we can actually arrest the temperature. Instead of going all the way from 50 to say 100 degrees Celsius, I can actually stop in between somewhere and come back. So it is also possible to fractionalize the total transformation stress by choosing the right temperature across the transition boundary. So this is something of course, for a well-known technique for vanadium dioxide, people have not done it. We are at least glad that we could actually identify and show that how the reversibly phase transformation can be probed using the well-known laser wafer curvature method. So again, I'm showing you one slide. the previously I showed you, the stress is plotted, the red color curve. We have clearly a tensile stress development based on the thin film thickness and quality. We have seen from 300 megapascal to maximum of around 600 megapascals of reversible stress. On the other hand, we can also measure the transport properties, simple IV measurement. We can again confirm there is a clearly around 3 to 4 orders, in this case around four orders of resistance change. So there is a clear correlation between the structural phase transformation, which is giving the stress, and electrical phase transformation, metal insulator transition, which is responsible for the large changes in the resistance. So the vanadium dioxide shows both electrical as well as structural phase transformation, which can be clearly established. In addition to that, we also wanted to cross-check, how do I know there is a phase transformation? I'm saying monoclinic and tetragonal. Of course, we have also done in situ TEM. We can again establish by electron diffraction, there is a phase transformation from monoclinic to tetragonal. For the benefit of time, I'm not getting into the TEM in detail. We also done the imaging, right? There are some contrast change we can capture during the phase transformation. So the question here is, I told you earlier, in the entire wafer curvature, thin film stress can be measured. But can we use in situ TEM during heating inside the transmission electron microscope? When I record electron diffraction pattern, when I also record bright field image, can I also try to visualize the phase transformation induced actuation? So what we have done, we have tried this particular method. In fact, initially, like this method, I would say I'm not very sure. At least in my understanding, it's something we have used the TEM for first time to get the actuation. It is inspired by the several negative results, because I want to actually see during the phase transformation, is there any twinning, right? I was trying to take bright field images as well as high resolution images. During the phase transformation, what I found, the imaging is almost next to impossible. You will see everything is perfectly in focus. The moment the phase transformation, right, starts, suddenly the sample just goes out of the focus. Right? I was initially like trying to kind of puzzled. Is there any thermal vibration, noise playing a role, and so on? But later on, I understood, of course, the whatever the thin film stress that we measured, that is what probably contributing. Your TEM sample is almost acting like a cantilever. Then finally, I decided to make a cantilever of vanadium dioxide deposited on the silicon substrate. I used the focused ion beam to make cantilevers like this. Of course, the cantilever is the edges, it is still electron transparent. The thickness, I would say, still it is slightly thicker. It's around 200 nanometer. So what we have done is instead of having a static sample, right? Of course, many of you are most familiar with the transmission electron microscope and the ray diagram. All I'm going to do is only one thing. Instead of having a static specimen, I'm going to put my cantilever, which can actually which can actually deflect during the phase transformation. So the height will not be exactly same. During the phase transformation, the sample can actually go up or down, right? According to whether I'm doing heating or cooling. So when the sample is going up or down, of course, I will not have the proper focused image, right? So exactly the focus would be changed, but the focus can be again corrected back with a use of defocus knobs. So every time what I'm going to do is I'm going to increase the temperature, maybe like in steps. Whenever the cantilever goes up, right? Accordingly, I would be able to correct back and bring the sample of the cantilever tip into the focus, note down the defocus value. Again, rise to the next temperature, iteratively, right, measure the defocus value. So the end of the experiment, we'll have a defocus value, how it is changing as a function of temperature. The same experiment I can do for tip as well as for the base, right? Any cantilevers, of course, when it is clamped, you will not expect, right, any deflection there. So the difference ultimately will give you the total actual cantilever tip displacement. So that is what's shown here. I'm just trying to show the bright field image. It is not the great quality image, but what we are looking at here is only looking at the Fresnel contrast. If it is out of focus, right, we have either like a over focus or under focus, right? So we'll have a clearly either the dark fringe or bright fringe based on the focus. So it is initially 62 degrees Celsius. And the sample is like, for example, slightly out of focus. I will change the defocus value, bring it back to focus again, then raise the temperature from 62 to 65. You can see here clearly the dark fringe coming, right? Again, take it, change the defocus, bring it to focus, raise the temperature to 67. So clearly by changing the temperature and correcting the defocus values, ultimately I'm able to get the defocus value as a function of temperature. And interestingly, in TEM, unlike other equipments, the defocus value can be controlled in a nanometer scales, right? Even few nanometer, I'll be able to fine tune my defocus value. So that way it is actually, I would say, relatively precise. We also did the other one. Instead of changing the defocus value, we also have a Z, as such the height can be also changed without touching the defocus value. I know the cantilever is going up. Okay, then I can correspondingly bring my sample down. So that way we can also have the change in height as a function of temperature. So both of them clearly telling me there is a abrupt change in the cantilever tip. As I said earlier, we can do the same exercise from tip and base. The difference will give me the cantilever deflection as a function of temperature. So going from insulating to metallic, otherwise monoclinic to tetragonal, there is around 400 nanometer or 400 to 500 nanometer of cantilever tip deflection. Of course, in this case, the length of the cantilever is much smaller, right? So like only like 5 microns and so on. So this can be manipulated further based on the dimensions. Again, using the modified Stone's equation, I can also calculate what is the transformation stress or the actuation stress, right? So we can see clearly this is the actuation stress around the 300 megapascal of tensile stress, which is almost matching with the wafer curvature measurement that I have shown earlier. Now, I want to like say the right this particular thing. Of course, TM is great. We can very precisely measure, even in principle, if you have a carbon nanotube. If there is a carbon nanotube coated with the shape memory alloys or the vanadium dioxide, like one side at least, even carbon nanotube deflection can be measured. But many of the bulk samples will have a really difficulty in preparing a sample, right? Making electron transparent cantilever for many samples may not be that easy. So we are thinking, can we use some other methods like nano indentation for measuring that? It doesn't matter whether it is a single crystal, bulk crystal, or polycrystalline material. Without having any thinning sample preparation difficulties, it'll be great if we can use nano indentation for actually measuring the actuation. That is what I'm showing here. Nano indentation, of course, I will explain in little more detail how we can measure the mechanical properties. In this case, it's a sharp tip, extremely sensitive. I'm going to just keep the tip on and just making a contact on my sample. So we have taken a vanadium dioxide micro beams of around 50 micron in thickness, and length can be like even millimeters to probably like 500, 600 micrometers. I know by EBST what exactly the orientation of the facet is. In indentation, instead of really, my idea is not to penetrate the sample and measure the properties. I just like like a blind man, because in this case I don't have a microscope. I'm using a stick, extremely sensitive stick, just to place on top of the well-defined crystallographic surface of vanadium dioxide. Say I'm applying just like as small as 10 micronewton or 25 micronewton load. After that, we are going to actually like raise the temperature, and we know, for example, phase transformation is going to happen between 65 degrees Celsius to 75 degrees Celsius. Keeping this particular load tip intact with the sample surface, if I change the temperature from 65 to 75, 10 degrees Celsius, maybe with a heating rate of 2 degrees Celsius per minute. In principle, if the sample is expanding, the expansion should actually push the tip up. If the sample is undergoing a contraction or shrinkage, the tip essentially should be pulled down. For a constant load, how the tip essentially can be displaced by the expansion or contraction of the crystal during the phase transformation, that is what we are interested in probing. I'm showing here the result, tip displacement as a function of temperature. I need to add a disclaimer here. We have not calibrated any noise or any other thermal effects. I'm at least aware of Professor Preeta Pant in IIT Bombay. There is a good piece of work in calibrating the thermal effects. In this case, we have not done that, but we have taken a standard sample. If I take a silicon crystal, single crystalline silicon, if I do the same experiment in the same interval, everything else is constant, same load applied, same temperature interval, I know this is the displacement or the distortion introduced by the thermal effect. It is going from 600 to maybe around 550 nanometers, right? The black color one. When I repeat the same experiment with the vanadium dioxide, you can see here during heating, right? This is a heating curve. Abruptly, you can see exactly very close to the phase transformation temperature. There is a sudden jump, around 600 nanometer of sudden jump in the tip displacement. So in this case, it is essentially like a result of the expansion that is taking place. As I said earlier, when the crystal is expanding, it is going to actually make the tip go up. In nano indentation, whenever we'll see tip is going down on the sample, that is noted as a positive signature. In this case, the tip is essentially going up. That is why the tip displacement is mentioned in the negative signature. So during heating, we have an expansion, and during cooling, the contraction take place. We're again able to capture the tip displacement. But exactly the tip displacement is not same in terms of the magnitude. I would say the expansion is more accurate, because when the crystal is expanding, it is going to push the tip up. The contact is always intact. But during the cooling, the contraction when taking place, there is a chance that the crystal may be disengaged from the tip. Right? There is a possibility of some error involved here. That is the reason we are seeing a slight difference in the magnitude of the displacement measured during expansion and contraction. Of course,
so
we can also
why
convert
is there a hysteresis?
Right. So this is a first order phase transformation. There are two things typically happens. In fact, hysteresis is very common in both electrical measurement as well as in the structural measurement. Like any other first order phase transformation, we have a delta T as well as hysteresis. Of course, there is some frictional forces involved during the phase transformation. So during the heating, the phase transformation temperature is 68 degrees Celsius. But during cooling, for thin film, the temperature could be at least 5 to 10 degrees Celsius lower. In single crystal, the hysteresis is relatively small. The temperature difference between heating and cooling can be as low as 2 degrees Celsius.
So this is polycrystalline sample.
So this is a single crystalline sample. The beautiful single crystal micro beams having, in this case, the orientation of the top surface also 0, 1, 1.
And this is freestanding. It is not on silicon.
So yeah, it is actually like because of nano indentation, we actually clamped it on the substrate.
Okay.
So right now it is just for the measurement to make sure there is no vibration. It is clamped. Otherwise, the crystal can be grown freestanding as well as on the substrate.
And so when it has to transform from monoclinic or tetragonal to monoclinic, the nucleation has to happen of the other phase.
Right.
And it happens at the boundaries, is it? At the grain boundaries?
So
if you have grain boundaries?
I have maybe in a few slides, I will show you the videos.
Okay, go ahead.
It's difficult to predict where it is happening. But what we have seen is it happens like a stripes. For example, like there is a crystal having the longer axis is say in the x-axis, the phase transformation goes like a strips parallel to the longer axis, the growth axis. I'll show you like in fact we try to probe both the nucleation stage is difficult. The growth kinetics, in fact, we try to probe by looking at the imaging. So like finally we could find around 0.53% of the spontaneous strain which can be reversibly tuned and also can be measured using the nano indentation. In my opinion, when you have a very small scales to deal with, actuation can be measured using TEM. If you have bulk material, in principle, we should be able to get reasonably accurate values using the nano indentation. So the last piece of work, of course, I'll also show some more videos for the phase transformation of VO2. In fact, like the reason I'm asking, can we reliably measure the properties across the phase change? So most of the time we do, for example, doing a micro indentation or nano indentation as a function of temperatures. But as correctly asked by Guru, we do not know where the phase transformation is nucleating and how the phase boundary is moving. So I'm doing an indentation, maybe taking the transition temperature from other measurements like DSC and so on. But locally, when we do measurement, no one can be actually like sure whether the place I'm trying to do indentation, whether already it is in the monoclinic state or tetragonal state or in the phase boundary. So there always can be a difficulty of measuring properties reliably during the phase transformation. So we also looked at the literature. Interestingly, though this material is known for 60 years now, the actual mechanical properties of vanadium dioxide, there is a huge scatter in the values. You will find the elastic modulus starting from as low as something around 70-80 gigapascal to around 300 gigapascals by first principle studies and so on. In fact, there are only few studies. Most of the measurements are limited to the room temperature monoclinic phase. Only few studies are actually there for high temperature phase. The last one is actually our own work. The high temperature phase also, like they have used the indirect method, like a resonant frequency measurement. When you have a cantilever of VO2 with respect to a substrates, a thin film, they are measured indirectly. And some of the methods also like based on thin films, VO2 coated on TaO2 and so on. So again, there may be a chance of substrate playing a role. So we thought why there is a huge scatter, can we use nano indentation, knowing that where the phase transformation is happening. And we are able to actually find the, I would say, more reliable results. We found around 17 gigapascal of change in the elastic modulus and 1 gigapascal of change in the hardness values. I will try to show this video. Looks like when I have the pointer, it is not allowing me to. It's interesting. So this is like recorded using the optical microscope during heating. So whatever the color change you see here, like let me repeat, initially it is like a white color. You can see like small lines, like stripes, essentially of gray color. That is essentially corresponding to the metallic phase. Again, there are some papers why there is an optical color contrast. As I said earlier, the optical properties also changes during the phase transformation. So the idea is like we know clearly, so relatively a large crystals, we know the where the phase transformation is actually happening. So it is possible to selectively do indentation. That exactly we have done. So for example, at 69 degrees Celsius, the entire crystal is insulating state. But within like a 0.2, 0.4 degrees Celsius, we can see a nucleation of metallic domain. And slowly the metallic domain is expanding and consuming the insulating state. So we have actually like confirmed it is metallic and insulating state by looking at the CV. IV measurement will tell us whether it is metallic or insulating. We also carefully looked at the Raman spectroscopy. In Raman spectroscopy, a metallic due to the polarization absence and so on, you will see the peaks will be disappearing. Whatever the signature peaks of vanadium, oxygen, the vibrational modes, they will be disappearing when it goes to metallic. So we know by Raman spectroscopy and IV measurement, it is metallic domain and insulating domain. And the growth dynamics also we know. Again, probably I'll skip the Raman spectroscopy for the benefit of time. After that, we try to do indentation from the insulating domain and the metallic domain. So we are able to clearly get this consistent values. As I said earlier, there is a 15 to 17 gigapascals of change. But in addition to changing as a function of temperature, measuring the properties in addition instead of as a function of temperature, we also have coexisting phases, like exactly this particular beam, say around 69.6 or 70 degrees Celsius. We can have metallic as well as insulating both the domains essentially together. So that way it is possible to do indentation across the phase boundary from metallic to insulating. That is what shown here. At constant temperature, we have elastic modulus abruptly changing when you are going from rotile phase to monoclinic phase. So we could actually clearly cross-verify both by the elastic modulus as a function of temperature and also holding on the same temperature, doing measurement from the metallic and insulating domains. We are able to get relatively consistent measurement. I would say the scattering is slightly more when you do just as a function of temperature, because sometimes we don't know the place we are trying to measure the property. Probably already it is transformed or at least going to be very closer to the interface. I would say the other measurement is a little more reliable without having the phase boundary and the complication of the phase evolution.
So Vishwa, is the orientation relationship known between the two phases, tetragonal and monoclinic?
Right. But the complete the orientation relationship, there is an excellent paper by Nano and so on. 011 of monoclinic goes to 110 with a clear matrix and so on. There is a nice paper. The orientation relationship is known.
Is that the reason why you have these at an angle, that the monoclinic phase is showing up at an angle?
Okay, so that probably, yeah, so I'm not very sure. So you are saying with respect to the, so we need to see more closely the crystallographic orientation.
How during because the it's a single crystal, you can see whether it is the angle at which you would expect.
Right. But if I go back to this particular video, here I can only see there are parallel to the longer axis. I'm not very sure the 45-degree, 40-degree angle is. I think it's a good question. I may have to think. Okay. At least we are not very carefully the angular relationship between the two phases in our imaging and measurements.
There were some that are coming up at 45. Most are at 9, like perpendicular, but some in your video do show up at 45.
Right. I think that's a very good point. Probably I need to check, maybe like doing EBST and so on, maybe more helpful. But you are right. By looking at the statistically, we can measure the angles and see whether it is matching with this orientation relationship or not. I have not done it, but I think it's a very good question. I will try to check that for sure. And finally, we also want to see like something more we can extract, because it is a metallic and insulating phases. We try to look at the pop-in event. The pop-in event, of course, can be correlated to the dislocation initiation or any cracking event and so on. Of course, phase transformation information you would get during the unloading curve if it is stress-induced phase transformation. But in this case, we are mostly triggering the phase transformation by the temperature. And we looked at the pop-in, exactly what is the pop-in load and so on. We found there is a statistically, the pop-in load, there is a difference between the metallic and insulating phase, at least around 1300 to 1500 micronewtons of load. In the absence of any cracking, we think it is maybe due to the initiation of dislocation. We also get some, we could not locate clearly any shear bands and so on, but some slip band kind of structures are available or seen in AFM and SEM. So we do think it is maybe due to the dislocation initiation. And at the same time, the fracture cannot be completely striked out. In order to capture that, we thought we can probably increase the load and capture. Just before that, I want to also show you, even during the phase transformation itself, the fracture is actually like known in single crystals as well as thin membranes. In this case, I have done the VO2 coated on a silicon nitride membrane, thin membrane. So just during the resistance measurement as a function of temperature, just like almost the transformation is about to get over, right? I would say slightly above the actual transient temperature. You can see the cracking pattern optical images also I have embedded here. It is started actually showing a cracks. Within like 2 cycles, we can see the entire membrane is completely fractured. So the fracture is something can happen during the phase transformation itself. People also shown when they try to grow epitaxial VO2 about 10 nanometer of critical thickness and so on, the epitaxial thin films also undergo cracking. Then we checked in literature, there is no single paper reports fracture toughness value of vanadium dioxide. Then we thought, why not measure the fracture toughness in single crystal by doing the indentation at monoclinic at room temperature, tetragonal at around 90 degrees Celsius. So the SEM images that you are seeing here, one indented at a room temperature, one indented at high temperature, but imaged at the room temperature. By again taking the crack lengths and so on, we are able to get the fracture toughness. We use the ANTIS model based on the C/A ratio. But only like one surprising thing is the reason I'm presenting here, of course, there is nothing new in measuring the fracture toughness. The fracture toughness values we measured like almost 2 years back. The student graduated, went abroad for postdoc. I was not confident in publishing paper. Of course, we have not published even today. The values are very, very low that you would expect for any ceramic material. It's like 0.045 and 0.083. There is a small jump, but the values are like anybody working in the mechanical behavior would immediately dismiss such a low values. I was asking the second PhD student to continue, again repeat. Every time she probably getting a small, like maybe in the second decimal, some changes, but it is not coming to closer to the actual values that we expect for the ceramics. If you look at the other ceramics, we know typically it will be like maybe 0.6 to 2-3 megapascal, m power 1/2. So we are no way actually close. Finally, we found the reason for such low fracture toughness values. You can see this is a vanadium dioxide grown on quartz substrate. The growth, typically the temperature is around 900 degrees Celsius. There are many of them already like having a cracks. I'm trying to open the pointer. So you can see here, many like lines that you see here, the line cracks are already there without even subjecting to any mechanical testing. Then we thought, okay, maybe like this is the reason the epitaxial thin films paper published in PRB, they are also seeing a cracking happening. So we thought thermal stress probably playing a role, taking the VO2 thermal expansion and quartz thermal expansion. We estimated the thermal mismatch and the stress. The stress is found to be around 0.95 gigapascal of tensile stress. So this is probably like already in a pre-stress condition. Some of them are probably already broken. Maybe the conditions are slightly less, slightly correct, and the thickness of the VO2 is slightly large. It can probably withstand slightly more load. So otherwise, what is happening is the nano indentation fracture toughness that we are measuring, we are not really taking into account already the tensile stress of 0.95 gigapascal acting on them, because we are doing the measurement on the platelets which are attached to the quartz substrate. Then we found a literature wherein the residual stress can be actually accounted in the entire formula. So if I add this residual stress of 0.95 gigapascal, then we calculate it is coming around reasonably like expected values. For a monoclinic phase, we are getting something around 2 megapascal, M power 1/2. and for tetragonal phase, we are getting 2.67. So there is almost like a around 30% enhancement in the fracture toughness, which may be explained taking the elastic modulus, otherwise the surface energies of monoclinic and tetragonal phases. I'm not very sure we have
If
time.
I can ask one more question, Viswanath, right here. You could also add the phase transformation stress to this, right? For T phase, possibly the fracture toughness is even more higher. You had about 300 MPa tensile stress.
You are very correct, very precisely said, because if you look at the residual stress, it is happening due to the growth. So taking the growth temperature and my room temperature, the residual stress is going to be common for both monoclinic and tetragonal phase. So for tetragonal phase, we have to add the transformation stress as well. So we exactly did that. For simplicity, I thought of avoiding, but very precise question. Only then we see this difference. If you don't add the transformation stress, you would not find such a large difference between the fracture toughness between the monoclinic and tetragonal phase.
Thank you.
Maybe I'll take maybe like 4 or 5 minutes just to quickly like snapshots of what I meant for manipulating the phase transformation with respect to strain. Again, a conventional top-down relation. Guru, is it all right?
Yeah, please go ahead. Yeah.
Right. So in fact, it's a very interesting, actually, like the stress temperature, this kind of phase diagram, starting from 2010 and so on. Already it is actually published in a few papers. As I said earlier, room temperature phase is monoclinic M1 phase. I have mentioned the space group for immediate for your reference. And I'm talking about thermally induced phase transformation going from monoclinic to rutile or the tetragonal phase, right? Like in the absence of any strain and or stress, the phase transformation temperature is around 68 degrees Celsius. But if there is a stress, for example, compressive stress acting, then the transient temperature keep on decreasing. Same way, if there is a tension, the tension prone to induce the phase transformation from M1 to M2. M2 is crystallographically different, but it is a monoclinic, space group is different, and it is also insulating. So the M1 to M2 transformation can be induced if you apply tensile stress, and M1 to rutile phase can be induced if you apply compressive stress. So taking this as a kind of a standard reference, there are several approaches people have tried it. By doping, of course, if you dope slightly heavier atom, like tungsten, for example, you can induce the compressive stress and accordingly change the phase transformation temperature. You can see in the DSC heat flow how the endothermic peak is shifted from 60 degrees Celsius to 23 degrees Celsius. The same thing can be done with the thin films having the lattice mismatch stress. You coat a VO2 on different substrate. By thermal mismatch, you can actually lattice mismatch and thermal mismatch. It is possible to tune the phase transition temperature. Same way, electrically the phase transformation can be triggered, and more importantly, the threshold voltage, right? Threshold voltage for the insulating to metallic phase transformation that can be manipulated. We have a strain. Again, compressive strain can reduce the threshold voltage from 8.7 volt to 2.5 volt. There are also interesting works on nano beams and nano wires. When you just bend with a simple help of tweezer, we can actually induce the phase transformation. Again, it's a very interesting subject. It forms a very periodic structures, the metallic domain that is nucleating in the insulating phase. Again, due to the surface and strain energy minimization, these kind of coexisting phases or phase evolution already demonstrated. So I'll give you 2 examples. VO2, we can deposit as a thin film on silicon. You can also make a VO2 sandwiched between 2 hafnium oxide layers. So because of the confined sandwich structure, there is a possibility of compressive stress acting on it. We have measured both resistance as well as temperature. We found the transition temperature is actually going from 61 degrees Celsius to 45 degrees Celsius. That is again a transport measurement. Structural phase transformation also we have seen by looking at the wafer curvature. Again, there is a change in transition temperature of 17 degrees Celsius difference. So whenever we take any heterostructure, one has to be careful, or one can also efficiently use this method to tune the phase transformation temperature. Again, I now have to make sure there is no chemical effect. We have looked at carefully the TEM cross section. There is no reaction layer. There are some evidence of Mori fringes, which might indicate there is a compression, but of course we have not quantified. And the second method is the doping method, already like established in the literature. We have again made a VO2 microcrystals doped with the tungsten. I think the DSC will be straightforward. Compared to undoped one having a 68-degree phase transformation temperature, systematically we can see it is going to 50 degrees Celsius, 41 degrees Celsius, 36 degrees Celsius as we change the doping concentration. Again, how do you know there is a clear phase transformation? We also confirmed with the Raman spectroscopy the phase transformation temperature indeed changes with respect to the doping. Again, tungsten being the heavier atom, it will actually induce the compression in the lattice. So that is something not probably new, but what is I would say new is we have also shown by doping how can you change the threshold voltage when you trigger the phase transformation electrically. So that is what's shown here. Undoped VO2, the threshold voltage, it is essentially like a simple current voltage measurement. Suddenly the current will increase because it is going from insulating to metallic state. That threshold voltage 2.27, we brought it down to 0.5 only by doping 4% of vanadium. Again, systematically we have compared 2%, 3%, and so on. So I think probably I may not have time. Like all I have to probably say with respect to 2D materials and so on. Extremely interesting to see atomically thin monolayers, how different allotropic phases can be manipulated by strain, because there is a shear force involved in many of these allotropic phases. There are some understanding, I would say more than understanding, there are lots of questions very similar to the vanadium dioxide. You can see here coexisting phases, allotropic phases can be captured using the fluorescent microscope. Having a same thickness in a monolayer form, you can actually manipulate the phases. There are several methods probably discussed. One other interesting observation we had, always we think heterostructures are actually going to have a problem of strain. But what we found, when we have a WS2 monolayer of only one phase, in this case 1H phase, during cooling, due to the tensile stress developed due to the thermal mismatch, it is cracking. You can see SEM extensively, it is showing a cracking. But when you have a coexisting phases, in this case, like we have 1H and 1T, there are two different allotropes. When they self-organize like this, during the growth itself, they have some compressive strain inbuilt. So this compressive strain probably somehow balances the tensile strain or stress, which is going to happen during the cooling when you do a growth at high temperature. So the heterostructures do not crack.
So
yes.
The 1H I can understand why it is showing hexagonal, but why is the 1T also showing similar facets?
So yeah, so in this case, the 1T is not fully grown. It's actually nucleating and growing within the 1H phase.
So initially it was 1H, so it was hexagonal, and the T is coming up.
T is coming. So only thing is we are able to achieve this during the CVD growth itself.
Mm-hmm.
There are some evidence of impurity playing a role.
Mm-hmm.
So we don't know exactly like when the transformation started and ended, but
Yes.
at the end product we do see this kind of a nice organization. I'll probably like stop here. We also done the manipulation using nano indentation for doing the sculpting that I described earlier. I'll just probably close the session. Just saying that there are several things that we don't know, especially like whatever the conventional understanding can be exploited for recent advanced materials like 2D materials and so on. And I'll stop here, and I'm happy to interact more if you have any questions. Thank you.
Thanks, Vishwa. Any questions or clarifications?
Can I ask a question? This is
Yeah,
Rita.
please.
Yeah. Vishwa, your nano indentation results that you were showing, no? I think it was slide 19. Sorry, I didn't write it down. Where you were showing the difference between the red curve and the blue curve, right? Where you said that in the red curve it gets pushed upward during heating.
The actuation, yes.
Yes. Yeah, this one. So
Right.
this is, you are doing this while keeping a load on the tip?
Yes, we keep the lowest possible load. We tried with the different loads. I think we tried with
Okay.
the 10 micronewton and 25 micronewton.
Okay.
We know like that whatever the penetration depth is very small in that particular load for VO2.
Okay.
After that, we are just essentially keeping the same load constant, only
I
changing
see.
the temperature.
The temperature. Okay. And during when the contraction happens during cooling, so the load doesn't, the tip is still in contact with the sample. I mean, somebody is monitoring that the load doesn't drop suddenly.
You are right. It did actually drops. So in fact,
Okay.
like the cooling experiment is much more difficult because
Mhm.
there is a definite chance of the tip getting disengaged.
Okay.
But what we did is we tried with the different rates. When
Okay.
we do probably like a very quick heating or especially cooling,
Hmm.
then the tip essentially get disengaged. When you do
Okay.
it slowly, since we are applying a 25 micronewton load,
Hmm.
that is able to follow it up to a maximum extent possible.
I see. Okay.
But in the
And
expansion, you are correct. Expansion is like definitely the contact is intact, but during the contraction, there is a chance of more errors.
okay. And since you showed later that, of course, you know, an applied stress will shift the phase transformation, right?
Right, right, right.
So here, this local applied stress of 10 micronewton or 25 micronewton, do you see differences, say, between the 10 and the 25 micronewton applied load
So
in
in
terms
fact,
of the
initially,
phase transformation behavior?
no. In fact, initially, we thought by indentation, we can locally induce the phase transformation. But
Right.
at room temperature, when I keep the single crystal, the kind of stress required or strains required is much more higher.
Okay.
So that is what like if you look at the phase diagram, it is also shown going from M1 to R
Right.
or M1 to M2, right? So like
Yeah.
typically it is if I understand correctly, minimum I think required probably would be almost like a 0.3 to 1 gigapascal.
Okay.
So like what we could do is when we go closer to the phase transformation temperature, like say around 55 and 60, then locally by
And then indent.
indent, then you see a change in the phase. So
Okay.
there is a trade-off between the temperature requirement and the stress requirement. At room temperature,
Of
even
course.
with the 6 millinewton, we are not able to find the
Right.
phase transformation induced, the stress-induced phase transformation in VO2.
Okay. And the other question I had was that does the sample plastically deform during indentation during this 10 micron and micronewton and 25 micronewton load? And
It's a
would
very
the plasticity play any role in the phase transformation? I mean, I'm thinking now in terms of this shape memory kind of transformation when people talk about, right? Then they don't like plasticity because they say this interface relationship gets disturbed and the going back and forth of the transformation gets disturbed.
right,
And you
right.
showed some very nice cycling studies on your films where you could just repeatably cycle. So I'm wondering that this indentation being very localized and I mean localized high load, Would it
Right.
induce plasticity, and what role would that play?
Yeah, that's a very good question. I remember, in fact, like for shape memory alloy, that one of the problem during multiple cycling due to the memory effect or plasticity effect, you would actually start seeing the compromise in the recoverable stress. Whereas for VO2, I would say that being a ceramic material, it has a relatively negligible plasticity. So the curve I'm showing here, it is like 2 millinewton. We have maybe around like a 30 nanometer the permanent deformation. So whereas the measurement that I was telling you about the actuation, there we are using much more smaller load.
I see. Those
So
are
like I
the
answer to your question, definitely there is a plastic deformation, but it is I would say negligible.
Just to maybe add on here, this pop-in event corresponds to probably a dislocation nucleation, right? And not a cracking event. In which case, possibly at 10 micronewtons, you don't have plasticity at all. Whereas if you cross over, then you will get a little bit of plasticity, but probably the density of dislocation that you're creating is still very small. And
Correct.
therefore, it doesn't really impact. Whereas the displacement associated with the phase transition is much larger and it's able to still show up.
Correct.
right.
Correct.
Yeah, actually, Jaya, what I was thinking was that if they played with different tip geometries,
Yeah. I
so
was also
very
thinking,
sharp
yes.
tips versus
Right.
more blunt tips. So Vishwa, the very sharp tip would give you more plasticity. I mean, the fraction of plasticity might be more blunt tip. It will be largely elastic. So, would you see effects of that in your measurements?
I think that's also a very good question. We have not done that. Probably like we do have a flat tip and a spherical tape. That's a very good, interesting question. We have not checked it, but definitely we can check.
Yeah, but even here, Preeta, if the 10 and the 25 are different or not, will already tell whether that has a strong role to play or not.
Okay.
Because at 10 you don't see plasticity at all. There is no pop-in. So I'm guessing that at 10 micronewton it comes back, whereas at 25 there is some 30 nanometer permanent
Right. The
displacement.
reason we thought of putting this, the histogram, it is like probably I should not go to the CRSS level, but like seems to be clearly the scattering, whatever we are seeing, it is happening consistently within the small window.
Right.
We found always it is above, like 1 millinewton or 1000 micronewton, between 1000 micronewton to 1500 micronewton. And within that, whenever we saw like a AFM and SEM, we did not find evidence of cracking. So definitely we do think it is something to do with the initiation of dislocation. And the difference between these two is probably very difficult to pinpoint. The scatter, we are able to see around 1500 micronewton of the difference. So yeah, so like pinpointing will be, I think, a little more difficult, but there is a difference in their actual threshold load required for initiation of dislocation. I think I don't have the values. Probably I thought, in fact, we have seen the elastic modulus harness below popping, above popping event. And also we try to calculate the shear stress. Probably the table I have removed it.
Vishnu, I also had a question about the transformation itself. Is it some kind of martensite-like transformation or massive transformation?
Yes, it's like as far as I understand, initially there was no clarity. For some reason, for example, zirconia, right? People would say it is a martensite. It happens at much higher temperature. For VO2, there was no strong statement, but recently there are many papers. Intensity phase transformation. Some of the kinetic studies also, the rate dependence and so on also seems to indicate it is a martensite phase transformation. There are few papers also established the twin boundary across the phase transformation as well.
Yeah, so I was about to ask, then in that case, they would see twin boundaries, right, to accommodate the
right,
deformation.
whatever the strains. Correct. But I
And
would say
how
still
much?
it is yeah, please go ahead.
Yeah, how much is the strain difference? Volume difference?
So again,
between-
the volume difference, it is actually like as per the literature, starting from neutron diffraction to many other measurements. It also scatter. There is a value varying from 0.3 to 0.55% of volume change.
Mhm.
It's like almost like the BCT, in all the axes, it is not uniformly contracting or expansion. In a C axis, it is going one way, and A and B axis other way. But there is a clear volume change of, I would say, 0.3 to 0.5.
And you also see variants because so it is going from monoclinic to tetragonal as you increase the temperature.
Correct.
So the tetragonals should be such that it should go back to monoclinic by the symmetry, the variants if you add up. Does that happen, or it is too complicated?
I think there is a one paper with elastic matrix and so on. They have shown the orientation relationship.
Mm-hmm.
I need to look whether we got into the level of variance. Even for example, the invariant plane strain and so on. Exact that kind of in fact the previous statement. What I want to make is many of the understanding what we have in metallurgy and say shape and realize. So that level of details are not done with respect to the phase transformation and the strain. Most of the work probably like a physics dominated. The metal-insulator transition is whether that is a Mott transition or a Peel's transition. That probably like several decades of fight. But I think the mechanics part and the microscopic, the origin of phase transformation with respect to tuning, the invariant plane, those things are, I would say, last few years I'm not very closely following up the literature, but I'm definitely tell you this is still inferior compared to the conventional understanding of the phase transformation.
Also, this that slide showed that your film was cracking, right? So, I mean, is it cracking? Hello, can you hear me?
Yeah, we can hear.
Membrane
Sorry,
one, right?
no. Yeah, the membrane one was cracking, right? So the cracking stress is sort of lower than the twinning stress here. Is that why it didn't accommodate?
Yeah, so in this case, actually, the cracking, in fact, if you look at very closely, the cracking happens only in the freestanding, the square membrane. The silicon nitride is actually a silicon substrate wherein silicon nitride is coated. This region is actually thick region, whereas the square, the interior region, that is a membrane. So in my opinion, it is actually like whatever the VO2 is imposing the stress, the membrane is not actually structurally stable to withstand. So it is not cracking other places, only the membrane is getting cracked. But
so the
in terms of
membrane is silicon nitride or the membrane is VO2? Sorry, I was confused.
So we have a 30 nanometer of silicon nitride membrane on which VO2 is coated.
Okay.
But I think still I don't have an answer for your question. What is the critical stress for tuning and the stress required for cracking? That differentiation also, in my opinion, it is not done. In fact, in the same paper, we also found a lot of tuning, but we are not very sure it is just a tuning associated with the phase transformation for the strain accommodation or crack-induced tuning. Because typically the crack propagation also, in fact, I tried with a high-speed camera, typically happens in the velocity of, like a sound. So there are papers due to the crack propagation, you may actually achieve the critical stress required to induce the tuning. So again, the paper, it was not very conclusive. We are just left with the observation of cracking and the evidence of tuning, but it was not, I would say, conclusive.
Okay. Any other question or clarification?
Sir, I have a question.
Yeah, go ahead.
In the in situ TEM experiments, I think slide 6, The deflection was,
Yes.
yeah, these deflections are measured from the cantilever, right? The cantilevers are made electron transparent completely. It is only the edge of the cantilever. I just want to clarify that.
Right. So we used focused ion beam to make I would say it's a relatively thick, but still we are able to see the grains and able to get the diffraction pattern. But otherwise, you are right. It's a electron transparent, at least to get the basic bright field and also to get the Fresnel contrast.
Okay, so the full cantilever is not transparent, only a portion, a small portion is transparent.
So the cantilever thickness, there may be a small gradation. You are right. The tip, it is in fact much thinner. Otherwise, also the entire. So this is I'm showing you the figure. It's a TM image, very low MAC image. We do have a electron transparency to get the at least basic bright field imaging.
Thanks.
Any other question?
Hi, Prabhakar here.
Yeah, yes. Go ahead, sir.
In your last slide, you have shown that this mystic state, thermal mystic state is 0.96 BPa. So it will lead to very high curvature. So when you are doing the institute TM also, the curvatures also lead to this bending. Whether you are considering that for defocusing?
Yes, so exactly. That's a good point. So that is what we are trying to do is we are trying to repeat the experiment. One from the tip. I do the same defocus, whatever I showed here, defocus as a function of temperature. We do measurement one from the tip, one from the base, where the cantilever is kind of clamped. So then whatever the curvature change because of the thin film deposition, right, those things can be like, normalized. Only the difference in defocus value for each and every temperature between tip and the base. That is what will give you the final cantilever deflection.
Okay. Yeah, that's okay.
Okay.
Maybe one more point that I wanted to ask on this indentation fracture toughness that you are looking at. The cracking pattern seems, of course, it is expected that it's going to be highly anisotropic. So you see it always aligned along certain directions and not in the others.
Correct.
Does it sort of correspond to the cleavage facets? And also, I guess that's also a reason why we get some differences from, like, I mean, these formulas which apply usually to homogeneous specimen. For single crystals, there are some more approximations that are done. But however, this is, I think, is a very good tool to measure. I mean, I'm also interested in measuring these kinds of things. We were trying to do it with freestanding structures to eliminate the stress effect. So it was very good to see it being measured and with the nano indentation tool itself. However, this problem is something that we always get questioned about, that these cracks are not in all directions and they are longer in one corner and shorter in the other. So
right. I think again, sir, very good question. Ideally, we want to actually rotate the crystal and see, with respect to the facet geometry. I'm not very sure if you can see this particular pointer here.
Yeah.
This is the crystal boundary.
Right.
So
Yes.
always you are right. The cleavage axis, at least in this particular orientation, we see the cleavage is happening exactly parallel to that.
Yeah.
In fact, ideally, we would have expected the crack to start to any of these corners, but rather it is actually trying to follow the cleavage or the crystal boundary. So for monoclinic and tetragonal phase, what we decided finally, we thought of doing systematically by rotation and so on, but we are not successful. We made sure both the crystals, for example, both the places, the geometry is not changed.
Yeah.
So that is you are right. Otherwise, it is going to definitely introduce a huge error in the measurement.
Yeah, it's actually good to, as a comparison tool, it's still very good, because if you want to say how much fracture toughness has changed by, I think it's still good. Basically, my problem is usually they get asked about the numbers itself. They're saying the absolute value that we are measuring is probably underestimating or overestimating, depending on how we.
Right. I think the orientation effect on the fracture toughness, it's going to be always a problem, especially for single crystals.
Yeah.
At least we did the EBST, we know what orientation we are doing indentation. Of course, you are right. The propagation also has its own dependence with respect to the orientation.
Thanks, Vishwa. I mean, very painstaking but beautiful experiments to see. So it was really something that I enjoyed listening to.
Yeah, thank you very much. I wish to continue interact with you more. Probably I am right. Belongs to the I don't know what to say, right? Like a material science, I try to do many things, but it is important to get critical comments from the experts. Especially, I know some of you are working on a very specific problem, more dedicated way. That would be like much required. In fact, this fracture toughness, even 2 years we suffered. Just we did not know we have to add this, right? The residual stress into the formula. In fact, he tried convincing me his measurements were correct.
Right.
But right, probably I would have got the answers. I wish much sooner after the experiment.
No, but you have done really, I mean, advanced experiments that we have. I don't think we have ever done here. So we have a lot to learn. Thank you.
No, I'm really keen. I know each one of you and your expertise. I'm definitely aware of. We should connect back. Same thing I was telling yesterday with a guru as well. I'll be more than happy to discuss and connect back.
Yes.
Any other question or comments? If not, I think we have spent about 1.5 hours. So yeah, it was a super talk, Vishwa. Preeta had to leave, so she left a comment in the chat saying that she had to leave, but she says thanks for the great talk, and thanks from all of us also for the great talk. It was really nice, and we will connect back sometime during the weekend.
Actually, I wanted to also bring this up that my student here, Nitin, is working on barium titanate structures. Very similar. We're looking at single crystal and these transitions and so on. So it was very useful for me to see what all can be done. And yeah, probably on that also I'll get in touch with you.
Yeah, I think Vishwa had enough for 3 talks, so he had.
Yeah, in fact, I was also worried. In fact, the carbon nanotube I mentioned, the mechanics, I could not even touch. Probably we should definitely
we should have more sessions to have a more detailed chat. So.
Yes.
Definitely. I'm actually right now missing the coffee with all of you. Coffee and follow-up discussion would have been more engaging. I'll definitely look forward to develop this conversation more bond stronger. Thank you, Guru. And
thanks a lot, Vishwa. Thanks for spending 1.5 hours from your busy schedule. I know that headship is a huge thing.
No, at least I will get an excellent sleep today. I have done justice to that.
That is for sure. It was a great talk. Yeah. Thanks, Vishwa. So we will get in touch. Yeah.
See you. Bye.
Yeah.
All right.